So today we are going to consider a new subject called continuous time Markov chain. Actually, in this subject, we are going to use property of exponential random variable, properties of some Poisson processes, and also you need to understand discrete time Markov chain. So I think this one is very actually ultimate goal in this course. Okay. So far we discussed discrete time Markov chain, right? Example of this type of stochastic process, wrapped one. Stochastic process defined on discretized time, and this stochastic process includes countable number of states, not just finite, countable. Okay, can be infinite but countable. Okay, and we are in Poisson process. We discussed about the stochastic process, which is defined on continuous time and include countable 0 to infinite positive integers as a state, right? Count process 0, 1, 2, 3, 4, 5, 6, 7, and so on. But the thing is, this event occurs at any point of time, continuous time. Okay, in Poisson process, always increases as time goes on. Now we are going to consider more complicated one. Okay, so transition can happen. So we can consider similar system we discussed in DTMC. The thing is, transition. Transition means transition of states can happen at any point of time, and in this case, we are considering continuous time horizon. Okay. And I'm going to define what holding time is later. Holding time is actually time until we leave the state. Okay. If we consider a certain state of the system, and then we are considering the time until we leave the state. Okay. Holding times at certain state are independent and identically distributed, and actually this one follows exponential distribution. Very important characteristic of the stochastic process. So we are going to consider such stochastic process. Let's consider an example first. So we are considering a machine. Okay, goes up and down means goes up. Going up means working. Okay. Okay. Working is working means it goes up. Okay. The state. One. And goes down means breakdown. Not working. Okay. So machine. We can observe. We observe. Yes, let's say we assume that we observe the state of the system. In this case, machine. Okay. And this we are considering two different type of states. First one, working up, right? And second one, not working, down. Okay. In downtime, a repairman tried to fix the machine. Okay. And then a certain amount of time, then we can use the machine again. So the state of the machine continuously changes. Okay, based on the structure. Okay. And then we have some assumption. Downtimes. let's say in this case di's are independent and exponentially distributed with mean 1 hour, and u sub I represent uptimes. Okay, uptimes. ui's are independent and identically distributed. It follows exponential distribution with mean 10 hours. Okay. Then how can you examine this system? The question is how can analyze the system? Okay, based on the structure of a stochastic process. Okay, when we consider stochastic process, let's say xt, unlike discrete time Markov chain, in the discrete time Markov chain, this random sequence is has this subscription n, right? N is the nth point of time, discretized time, right? 0, 1, 2, 3, 4, and so on, right? But now we are going to consider continuous time, 0 to infinite. Okay? So now we are going to denote a process as a function of t, so large X of t. In this case, represent state of the machine. State of the machine. How many different type of state we have for machine? 2. First one, up, and second one, down. As we did before, we can describe the such case like down can be denoted by state 0, and up can be described as state 1. So we have 2 different type of states. Okay. In this case, we can describe this x of t as number of machines at t, which is working at time t. The same meaning, right? Because down state, we cannot use any machine, but up state, we can use the machine, right? So 0 or 1. We can define 2 different type of, we can use 2 different type of description for x of t in this case. Okay? And then, let's say we observe downtime and uptimes. Di represents downtimes, and iid, this one iid exponential rate is 1. Okay, and ui represent of times. This one is iid exponential 1 over 10. Okay, and then we can keep track of state of the system. Let's say as time goes on. Okay, large x of t can be 1 of 0 and 1. Let's say, let's start with 1. Okay, then the first time we can consider the system which is working during U1 one amount of time, and then break down, repairman start to fix it, and then a certain amount of time, let's say this one D1, and then working again, and so on. Okay, this one shows state changes as time goes on, right? You can keep track of the numbers. The thing is, they are means U1, U2, U3. They are IID exponential exponential random variables, and T1, T2. They are also IID exponential random variables. Okay. So different from unlike Poisson process. In the Poisson process, this graph always increases as time goes on, right? At a certain point of time. But now we are going to consider one of the state and holding times, and then change the state, holding times, and then change the state, and so on. Okay. As we discussed in the discrete time Markov chain, ultimate goal of this subject is how to calculate transition probability. Okay, transition probability. But in this case, this transition probability might be function of t. Okay, even though we consider a transition from a state to another state, but this transition probability might be the function of t. Depends on t. Okay, and then we are going to consider existence of stationary distribution. If there exists unique stationary distribution, then we can calculate the long run average numbers, like long run average cost, profit, throughput, holding time, and so on. Okay. So when you try to calculate such measures, first we need to understand what x of t is under certain conditions. Okay. So we are going to consider. So as I mentioned before, we are considering a stochastic process with two important ingredients. First one is holding time, and second one is Rodman matrix. So holding time means for each state, okay, each state before until we leave the state, we can consider the amount of time, right? This amount of time are IID for a certain state and exponentially distributed. Okay, for each state. Okay, for each state, we can consider amount of time we are in the state. Whenever we change the state, then we need to consider different state, and so on. But for a certain state, this time is called holding time for a state. The state. Holding times in CTMC, continuous time Markov chain, this holding time follows exponential distribution. Okay? And Rodman matrix is transition probability from state I to state J when state is firstly changed from I. So we can keep track of the state on the continuous time. Okay? And at a certain time, we found that this state changes. Then, based on this Rij, okay, this transition probability, state changes. Okay. Okay. So in this example, the simplest one, we are considering two different states. Right? Two different, up or down, up, down, right? Up, down. Let's try to define holding times. Okay, holding times. say T1 represent holding time for state 1. How can you define T1? This one is actually the same as UI, right? And T0, how about roadmap matrix? So, whenever, let's assume that we are in the state 1. Whenever it changes, then state changes to from 1 to 0 with probability 1. There is no other choice, right? No other choice. There is just two different states. So with probability 1, so 0, 1, 0, 1, diagonals all 0, right? Since we are considering the situation which when we try to leave the state, so not come back in this structure. So 0 to 1, 1, 1 to 0, 1. This one is actually roadmap matrix of the system. So now I'd like to introduce the definition of continuous time Markov chain. Actually, we can consider the same condition for the condition 1 as the discrete time Markov chain. So for all time index, in this case t rather than n, x of t is one of the state in the state space we define for the system, large S. Okay, and the second one we call this Markov property. Okay, but the thing is, since we consider continuous time, okay, we are not considering just one step after, before, and so on for the transition probability. Okay, the past represent all the state from time 0 to time S, but S is not included. Okay, continuous time. Okay, but S is not included. And then since we assume that this time S represents current time. Okay, and then large time t, positive value, a certain amount of time later, what is the probability that the state is J under this condition? This probability is independent of all the state from time 0 to S. S is not included. Okay, we call this Markov property for continuous time Markov chain. Okay, and we can consider so different type of continuous time Markov chain, but in this course we are going to consider stationary transition probability, which is defined as follows. Okay, so we call this x of s, given that x of s equals I, current state is I, what is the probability that x of s plus t is j? I mean, time t after, what is the probability that this state is j? We are going to denote this by large piece of ij of t. As I said before, in continuous time Markov chain, this transition probability is actually function of t. Even though we specify I and j, okay, this is not just one step after. we can consider any amount of time t after. Okay, what is the probability that state is j, given that current state is I? Okay. As long as t is fixed, then this value can be fixed independent of current time. Then we call this stationary transition probability or homogeneous transition probability. So this one is not this is not dependent of S, this probability, current state, any point of time. Okay, this probability only depends on current state and the next state we are considering and the amount of time. Okay, we call this stationary transition probability, and we are going to consider all the continuous time Markov chain in this course is stationary or homogeneous transition probability. Okay, this is new one. This is new one. Okay. So when we consider discrete time Markov chain to examine the system or chain, we usually working on transition matrix, right? Transition matrix is actually transition probability, one-step transition probabilities from older state to another state. So size of the matrix is number of states by number of states, right? Generator matrix is quite different from transition matrix. Actually, this matrix does not include any probability information. Okay? Not related to any probability relation. Actually, this concept of the generator matrix is this matrix includes all the information of holding times and the Ludman matrix. Both informations are in the matrix, just one matrix. We call this generator matrix. But the thing is, this one is not about probability. Okay, so I'm going to show you how to construct generator matrix based on these informations. Okay, if we have all the holding times, actually holding times follows exponential random variable distribution, right? So as long as we can define this rate of each holding times, then that's fine. Okay, let's say this one is lambda I. Lambda I is rate of holding time for state I. So we have number of state. The same number of this lambda I. Number of lambda i's is the same as number of states, right? Each state has rate lambda I, and Rij represent the element in the i's row and j's column in the Rodman matrix. Then lambda ij can be defined by negative lambda I when I equals j. So all the diagonal part might be negative lambda I. Off diagonals, lambda I times Rij. Okay. So we are going to consider it. We are going to apply it to two examples. Okay. Okay. Then why do we need to consider such matrix? Why? Because later we want to calculate transition probability for a certain time t and state I and j. And we want to determine whether the unique stationary distribution exists or not. And if yes, then we want to calculate it. We want to find it. Why? Because we want to calculate long-run average measure. That's the ultimate goal of the material subject. Okay. And to do this, we need to use generator matrix rather than holding time or roadmap matrix. As long as we can get generator matrix, then we have a chance to calculate transition probability for a certain time t. And we have a chance to calculate stationary distribution of the chain. Okay? So, in the continuous time Markov chain, to calculate transition probability, we are not going to use roadmap matrix or holding information of the holding times. Okay? Directly. We are going to directly use generator matrix. When you try to find stationary distribution, same. We are going to use generator matrix, not roadmap matrix, not transition matrix, not holding time information. So, matrix with lambda ij called generator matrix. We can skip it. So based on the structure, as we did in the discrete time Markov chain, okay? So we can describe the chain with the one-step transition probabilities, transition matrix. Another way, we can draw transition diagram, right? Similarly, to examine continuous time Markov chain, we can construct generator matrix, or we can draw rate diagram. Okay. So node of the rate diagram is each node represents each state, and arc represents lambda ij, transition rate, okay, in the generator matrix. But we don't consider any self-feedback. That means we are not going to consider any information in the diagonal of the generator matrix to construct such diagram. But we assume that we have the information for the holding times. So this diagram and the information of holding time include all the information in the generator matrix. Okay? As we did before, instead of using generator transition matrix to calculate stationary distribution of the DTMC, we can use transition diagram, right? And the cut method, do you remember? Yes. Similarly, to calculate stationary distribution of the CTMC, we can use generator matrix, or we can use rate diagram and cut method. Very similar. But the thing is, information in the rate diagram is different from information in the transition diagram in the DTMC, and information in the generator matrix is actually different from information in the transition matrix. Okay. So let's consider some examples how to use it.